So earlier in, not this century, but the century before, so the 18th or 19th and 20th centuries, they started to arrange atoms or elements based on different properties. The properties they were looking at were stuff like hardness, compressibility, boiling point, it's going to say BP, melting point, density. What they found is when you arrange these against, at the time it was against mass, what you find is you see that there's a lot of trends. There's a periodic nature where we start moving, going down, and we see they all have a certain direction. Things were going in a certain direction, and then all of a sudden it would start again, and we go like this. And what that told us is there was a periodic nature to how atoms exist and the behaviors they exhibit. So that's why we call it the periodic table. Because of the periodic nature of atoms with chemical properties. So as people started seeing, scientists started seeing the different properties that exist, they started arranging things in different rows, in different columns. So that as you move, so we're up periodic table. So as you move along the row, you see a certain trend. As you move along rows, and you see different bonding properties as you move along columns. We now know, because we've been looking at it, the electron configuration, that has a lot to do with it. If we look at all of the group 1 elements, we know that they all have like an oxidation of +1. They're all valence electrons, or all the S1. So because of that, they're going to have similar bonding properties. And then as we move along a given row, we all have this, we're all in the same shell, with the same principal quantum number. So if we look at row 4, we know that n equals 4 for all of those rows. They're going to have certain chemical properties in terms of mass and density. So the big trends that we're going to look at in this chapter are the metallic character, the metallic character is whether something is a metal or not, shielding, which I'll get to what that is in a minute. We're going to spend a lot of time on shielding and screening. That is essentially how well core electrons screen valence electrons. And this is going to lead directly into atomic radius, and then ionization energy, I'm just going to call IE, ionization energy, electron affinity, and electronegativity. So for the exam, you're going to need to know these. We'll get to these three, or Ryan will get to these three next week, but those won't be on the exam. So first, let's talk about metals. So, what's a metal? Well, first of all, it's a good conductor. They're malleable, smoothly shaped, at least when they're hot, and high melting point. It's really hard to make melt. Non-metals, on the other hand, the opposite of that. So, they're weak conductors. They're not malleable. Their melting points are really low, where they're gases. So the periodic table is arranged so that it's very easy to tell metals from non-metals. So this is very crudely drawn, but it's good enough for this. Metals, metallic character, goes up as you go to the left. So that the most metallic things are over in this corner right here. Non-metals go to the top right. And then there's this in-between right here. So you can see the red line on the periodic table, that staircase. That's where your mixes, your metalloids are. So they're like a mixture of metals and nonmetals. So what makes a metal? Well, metals generally want to lose electrons. They want to ionize into plus, give off an electron. Non-metals, we'll call it NM, want to gain electrons. That's pretty much the basic definition. Now, why is this though? Why do metals want to lose electrons? Why do non-metals want to gain electrons? Well, it's all about being as stable as possible. And which atoms, if you look at just an atom, which ones are going to be the most stable? Looking at the periodic table. Which column? Yeah, the noble gases. And that's because their electrons, their valence shell is full. So they have the most stable electron configuration. So metals lose electrons to attain noble gas electron configurations. Non-metals are just the opposite. Gain E. So that's the base definition, and that's pretty much why why metals behave the way they do and non-metals behave the way they do, is because whether something wants to give off electrons or whether it wants to gain electrons. So the examples we have, chlorine is a non-metal. So chlorine, what it wants to do is gain an electron at the minus. As soon as it becomes at the minus, it goes from an electron configuration of helium, 2s2, 2p5, to an electron configuration of neon. So in terms of the electrons in fluorine, it would much rather have this neon electron configuration than this helium with 2 electrons, or 2 s electrons and 5 p electrons. Lithium, on the other hand, would love to give off its electrons, lithium plus. Lithium has helium, 2s1. And as soon as it gives off that s1 electron, it now becomes just helium in terms of electron configuration, which is much more stable. So we can even look at something more complicated like calcium. Calcium is going to be Ar 4s2. And it's going to give off an electron to become calcium plus an electron, so that's going to be Ar 4s1. Now that's still not a noble gas configuration, so it's going to give off another electron to become calcium 2 plus. Now it has a noble gas configuration. So that's why calcium loves to have a 2 oxidation. So now it's a noble gas. So, as with everything, there's exceptions, and of course, our exception is the transition metals. Some of them like to lose a lot of electrons in order to become a noble gas configuration. So, the example is manganese, 4s2, 3d5. When it's neutral, it loses 7 electrons, and it becomes just like argon. So it formed a noble gas. Copper, on the other hand, does not like to do that. it likes to lose 2 electrons. As you know, copper 2+ is very common. So you start out at argon 42, 3d9, or actually, sorry, 41, 3d10, it's the exception, it's group 9. And it goes to 3d7. Or sorry, 3d9. Loses 1 that is wrong. It loses 1 s electron and 1 d electron, becomes 3d9. That doesn't look very stable, but apparently it is. It's kind of the exception. Just metals have exceptions. So normally metals lose electrons, if no low gas configuration, non-metals gain, and transition metals kind of do in between. Yes? Yes, all of them. But not all transition metals do that. All right, so now we're going to get to a very complicated topic of electron screening. So we're probably going to spend the rest of the time talking about electron screening. Difficult concept. So there's screening, shielding, and how it relates to atomic radii. Okay, so the first thing actually we need to talk about is atomic radius. So atomic radius is defined as, here's our 2 nucleuses. It's half the distance between 2 nuclei. So if this is d, the distance, the radius is going to be d divided by 2. So what kind of nuclei, might you ask? Well, it depends, because there's different definitions of radii. So you could have the radii when you have 2 nucleuses that are ionically bound. So this is like an ionic bond. So it's going to have a different radius than a covalent bond, which shares electrons, so it looks a bit more even. And then lastly you have, so there's ionic, there's covalent, and then there's metallic. So each one is going to have a different radii. So it's important when you compare radiuses, or radii, which we'll do, that you always use the same one. So most of the ones that you'll see in the book are for covalent bonds. So we'll just compare covalent radii. Now, what are the units we're going to talk about with radii? Well, there's 2. I have to bring, the one we're mostly going to use is angstrom, but I'm also going to talk about picometers. The reason I have to talk about picometers is because it's an SI unit, it's an SI prefix, so it's technically the most correct version. And that's 10 to the negative 12 meters. The problem is, atoms are not really that size. The size they actually are angstroms. So we're going to talk about angstroms, which is this A with the circle on it, and it's 10 to the negative 10th meters, which is just like perfect to talk about the distances between atoms. Because when you talk about angstroms, it's like 1 or 2 or 3, instead of picometers, 100, 200. So that's the nomenclature for what we're going to be talking about now. We're going to move on to shielding. So I'm going to draw a very simplistic atom. This is not correct. It's going to be a Bohr model, so you know that electron wave functions are very complicated. This one should be very simple, where we have in the middle, here we have our nucleus. And right next to the nucleus, there's a lot of 4 electrons. And then, so they take up all of this space in here. They exist there. And outside of the core electrons, we have valence electrons. Now, what are the valence electrons? Well, let's look at, say, magnesium. So magnesium has an electron configuration of neon and 3s2. Now, the noble gas neon is what makes up the core electrons. So core electrons, previous noble gas configuration, or noble gas electrons, which are in a noble gas configuration. And then all the other electrons, so in this case, the 3s2, are valence electrons. So when we're talking about atomic radii and we're talking about things bonding, we're not talking about the core electrons. What we're talking about are the valence electrons. Those are what actually determine size, not the core. So those are the ones we're looking at. But it turns out the shape of the core electron and how many there are will affect the valence electron. And the reason is because of screening. So what we're going to bring up is the topic of ZF, which stands for Z effective. So the valence electrons will see the nucleus, but because of the core electrons, it won't see all of the nucleus. It'll only see part of it. So the Z effective, which is the amount of the core that our valence electron sees, is equal to the total charge in the middle minus S. And S is the screening. So for the example of magnesium, there is 10 core electrons. So 10 core electrons, 2 valence electrons. Now this is an approximation, not technically correct. If we wanted to look at the ZF of that, we'd say it's equal to the charge, 12, minus S, the number of screening core electrons, which in this case is 10, because that's what electrons are in neon. So we get that the Z effective is 2. So that the valence electrons in magnesium only actually sees a charge of 2. Now what does that do when it only sees a charge of 2? What's drawn on the picture? Here's magnesium. It has the Z equal to, this is Z equal to 12. So if you had 2 electrons here and it saw Z equal to 12, it would hold the electrons pretty tight. That's because there's a lot of charge. So as you know, electricity, magnetism, when you have opposite charges, positive protons, negative electrons, the higher the charge, the tighter it's held. So the attractive force is proportional to Z. So as Z goes down, so in the case of Z equals 2, Z effective equals 2, you get that now our electrons go much farther out. So this circle became a lot bigger. So as you increase the screening, Z effective gets smaller and your atomic radius gets bigger. Let's draw lithium, which is much smaller. So lithium, if you just looked at lithium by itself, it has Z equal to 3. Its outer electrons would maybe be, or outer electron would be here. But though, because there's 2 core electrons in helium, with the Z effective equals to 1, now your electron's much farther out. So this would be what you'd expect if you had a full core of 3 protons, and this is what actually happens when you have the core screening. So this is a pretty important concept. There's 2 things to notice is that if you have a stable configuration, so you have a noble gas, those are the best at screening. The valence electrons don't screen very well. So as you move across the periodic table, let's say we go with phosphorus 15, with chloride 17, we're gaining electrons, but those electrons that we're adding are valence electrons, therefore they don't screen as well. So let's look at the periodic table and see if we can make some kind of trend out of this. So let's start at sodium and we'll move across to argon and see what happens to the screening. So if we look at sodium has a Z of 11, the electron configuration is neon 4s1. We look at, I'm just going to skip the phosphorus, that's neon 4s2. Okay, this is 3. 3s2, 3p3. That is a charge of 15. Okay, so what is the ZF for both of these? Z effective for this one is going to be 11 minus, and this is a rough approximation because it's not actually going to be the exact number. It's going to be around 10 because it's going to be around the number of electrons that neon has. So this will be a Z effective of 1. Now the Z effective for phosphorus, though, is going to be 15 minus, again, 10. Because it hasn't gained any core electrons. The only electrons that it's gained are valence electrons. And as I said before, valence electrons don't do a good job of screening. So this is around a ZF of 5. And this is very approximate, because these aren't actually going to be 10 and 10. But the idea is, as you move from left to right in the periodic table, the Z effective, which is how much of the core the electrons can see, it gets bigger. And what happens as you move to the right, what you're going to see is the electrons move closer. Because ZF is going to be getting bigger as you move from left to right. When ZF gets bigger, electrons are held tighter. And when they're held tighter, that means the atomic radius decreases. So that's a general trend you'll see in a row, that you go from left to right, you see that the electrons are going to see more of the core, and as they see more of the core, they're pulled in, and when they're pulled in, the entire size of the atom gets smaller. So things on this side of the periodic table are bigger than things on the right. Within a row, though, within a row. Because as things move down, they get bigger. The reason why they get bigger is because you're just adding more quantum numbers. So you're just adding more shells, and when you add more shells, you're going to get bigger sizes. So if we look at the simple example of lithium versus sodium, so lithium, you have your shell, you have 2 electrons, and 1 electron. Then you look at sodium. Even though some of these electrons will actually be tighter, you now have this 3rd shell. So when you start adding shells, things are naturally going to get bigger because they're just not held as tightly from the nucleus. So down a column, radii increases. So are there any questions on this? So that's a good question. Somebody asked, what do we use for S? How do we get S? The short answer is you won't need to calculate S, or you won't need to calculate ZF. I'm doing this to give an example of how to show that as we move from left to right, ZF gets bigger. But in general, you won't need to have a quantitative number for how small things get. What you will need to know is look at the trend in the periodic table. That is, ZF gets a lot bigger as we move from left to right. So you won't need to calculate S directly. Okay, let's talk about exceptions. Transition metals. This will probably be on the test. So, you know how I just said in our periodic table that I drew, atomic radius gets bigger, or sorry, smaller. Sorry, atomic radius smaller Not true for transition metals. The main reason is your valence electrons for, let's say, for row 4, so that vanadium, chromium, the valence electrons are actually going to be your 4s2 in that case. But when you add electrons, you're adding it to the d. So when you're adding electrons to the d orbitals, they're actually on the interior. So because they're on the interior, you're not really changing, you're adding more electrons to the core. So you're adding 4 electrons, which if you remember, ZF equals Z minus S. So as we move from left to right, Z is going up, but so is the screening, because you're adding the same number of screening electrons that you're adding of your, that your nucleus is getting bigger. So nucleus, charge rises, but so does the screening. And that's because we're adding to core electrons as opposed to valence electrons. Okay. Lastly, we're going to talk about the relative sizes of ions. So what happens to the sides when we start to create ions? Let's first talk about cations. So when we lose electrons. Well, what happens when we gain a cation, or when we lose electrons, is we have less other electrons. So charge of nucleus appears greater because we have less electrons there to get in the way. So since the nucleus now looks bigger and more powerful, it's going to pull the electrons in more, so atomic radius gets smaller. And you could say that's because of stronger attraction by the nucleus. So what happens when we gain electrons? In this case, we're actually adding electrons. So the nucleus, there's other electrons getting in the way. So electrons interfere with each other. Specifically, how they feel the nucleus. Therefore, radius gets larger. So when on the left side of the periodic tables in group 1 and 2, when those lose electrons, they get really small. But on the anions on the right side of the table, when they gain electrons, they get really big. We have a picture for this. So here we see both the neutrals. The neutrals are in red. And then we see the anions. So as we can see, the cations, when they start losing electrons, they get really, really small. And the anions, when they gain, they get really, really big. I think there's a figure like this in the book. Cool. So I think that's it.